Alrighty guys, we are on our last video notes. 11.3, this is volume using known cross sections. Known really just means that it's going to tell you which type of shape that we are going to be dealing with. So the three that we're going to be seeing are squares, semicircles, and equilateral triangles. Okay, so this is an extension of the disc and washer volumes, except now it's different cross sections. All right, so before we do anything, I just wanted to refresh our memory on some area formulas. The area of a square, right? We've got a square here. Let's just use b to represent the length of the sides. B times b is going to be b squared, right? That's the area of a square. Area of a semicircle. Okay, semicircles like this, where this distance is r. So the area of a circle is pi r squared, so half of that is pi r squared over 2. And another way to write that is 1/2 pi r squared. Okay. And the last one's an equilateral triangle. You might not know this, but this is something that's going to have to be committed to memory. An equilateral triangle just means that all these sides are the same length. So say this is A, and this is A. Okay. So after a lot of algebra and some trig, what you get out for the area is the square root of 3 over 4 times a squared. And that would be our area formula for an equilateral triangle. Okay, so looking at this, essentially what we're going to be doing, just like we did with the disc and washer methods here, is we're finding the volume of solids with known cross sections. Okay, so there's two different ways to do this. When the cross sections are perpendicular, okay, so that means like 90 degree like this, perpendicular, okay, to the x-axis. Our volume equals the integral from a to b of the area of the x variable we're dealing with, dx. Okay, so it's basically taking the integral of the area to get to volume. Okay, and now the other way is exactly the same, except it's when you're taking cross sections of an area with respect to y. So with respect to the y-axis, right? Taken perpendicular to the y. Okay, so again, perpendicular is just 90 degrees. And it's the same formula from, endpoint to endpoint of the area, but instead of your variables that it's with respect to x, it's now with respect to y. Okay, so really the process doesn't change. You just have to make sure you pay attention to when it says perpendicular to x versus perpendicular to y. Okay, so let's take a look at this first example. This is asking us to find the volume of the solid in which the base is the region bounded by these graphs. Okay, so first off, let's get a picture of f of x, g of x, and x of 0. Well, x of 0 is right here, right? That's x of 0, okay? This is f of x, so again, you can create a table here and plot it. Okay, so we're starting at 0, right? So we may as well start at 0. Plug 0 in, I'll get 1. That's here. If I plug 1 in, I get 1 over 2, so 1 minus 0.5 is 1/2. Okay, so that's here. And I do 2. 2 over 2 is 1. 1 minus 1 is 0. Okay? And what you'll start to see is that's just a line, right? So that's f of x. We can repeat that for g of x. I'm going to do the work over here. So g of x equals -1 plus x over 2. Again, start at 0 because that's where we're bounded by. Plug 0 in, you get -1. If you notice, these are the same. It's just the opposite direction, but we'll keep going anyways. 1, -1 plus 1/2 is -1/2. That's here. And then 2 brings us to 0. Okay, and that's where they intersect. Okay, so this is g of x. All right, so the area that we are looking at here is this, right? So you see that the base here the base of our solid that we're dealing with is a triangle. Okay, so this is the base. And then it says that we want to use cross sections perpendicular to the x-axis that are squares. Okay, so I'm going to try and draw a 3D picture of what we're essentially going to try and do here. So if this is our base of our triangle, or of our solid, right? Essentially what we're trying to do is find, well, perpendicular, right, to the x-axis. That's perpendicular to the x-axis, right? 90 degrees perpendicular to the x-axis. So essentially what we're doing is we're finding, if we were to raise this up, so we're basically bringing this up, 3D version of it, right? These have to be squares. These 3D versions have to be squares. Right now, that looks like a rectangle, but if I bring it all the way up, then maybe it'll be the same height. Okay, so I'm going to try and draw a 3D picture over here where we've got essentially this raised, right, triangular solid, okay, where this is our base, right? And then what we're trying to do is we're trying to find the little area between here. Now it's kind of hard to see, okay? But we're basically taking out little slices of squares. Okay, we're taking out these little pieces of squares each time, right here, here. We can do it over and over and over again until we get the entire area, all right? So we basically have to figure out, we know that the volume, what we're looking for, is equal to the integral from a to b. Now that's easy to find because it's literally from 0 to 2, okay, of the area with respect to x dx, right? Now this is the hard part here, the area of x. But the area of x is just the area of our cross section, okay? So this area and these areas in here, in these things, a of x, it's the area of our cross sections, okay? Which is why I reviewed these formulas over here, okay? Because it said we have squares, cross sections, okay? And I know it's perpendicular to x, so I'm using with respect to x. So the area of a square is b squared, right? Or length squared, whatever squared, okay? So we just basically have to figure out, well, what's b in the context of this shape right here, right? What's b? Well, area of a square is b squared, right? Well, the length here of this square, right, this length, isn't it just this point on this function minus this point on this function, right? It's this minus that. That'll get us that length, okay? So really, b is just my top function, f of x, minus my bottom function, g of x. That's what my b is, right? And then I squared it because that's the area. So it's really just this function minus that function to get that length right there, okay? So if I were to do some substitution here, what do I know f of x equals? Well, I know f of x equals this. Okay, minus, what do I know g of x equals? Well, I'm going to distribute the negative as I go, so plus 1 minus x over 2, and then we have it all squared, right? And this is our area in terms of x, okay? And now we're almost there, right? So I basically just have to take this, right? and plug it in right here. Okay, I'm going to do that work on a separate sheet of paper down here. So I know that my volume equals the integral from 0 to 2 of, I'm going to combine 1 plus 1 is 2, right? And then this becomes negative 1 over 2 minus 1 over 2x. So minus a full x, and all of that is being squared dx. Okay, so I just simplified this. Okay, I can show you how. I just did 1 plus 1 minus x 1/2. This is all squared, right? And then 1 plus 1 is 2. And then negative 1/2 minus 1/2 is a full negative 1x squared, right? And so that brings us back to here. Okay. Alrighty, so now from here, all we have to do is integrate. So there's a lot of different ways you can do this. I think the easiest is probably just to multiply this out, right? So I'm going to take the integral from 0 to 2 of 4 minus 4x plus x squared dx. Again, I just multiplied 2 minus x times 2 minus x out. Okay, and then integrate separately. You should be getting reverse power rule. This is to the first, so 4x minus 4x squared over 2 plus x cubed over 3, and then fundamental theorem of calculus, integrating from 0 to 2, right? Okay. You can simplify this to 2. That'll probably make your life a little bit easier. So if we want to do, again, fundamental theorem of calculus, f of 2 minus f of 0. Okay. Where f of 2, we plug in wherever we see an x, a 2. Okay. Minus f of 0, which honestly is just going to be 0. There's no point in going through that. Okay, and then when you simplify everything out, what you will end up getting is 8 over 3. Beautiful.